we have a problem, no? A jet, okay? A jet having a diameter of 50 mm and a velocity of 50 meters per second is deflected by a vane which is curved through an angle, no, of 60 degrees, which is moving with a velocity of 6 meters per second in the same direction as the jet. Now, determine the x and y components of the force exerted by the jet and the direction and the velocity as it leaves the vane. Okay. So, let's try to label our free body diagram here. Now, we have 50 mm, so that will be the diameter of our nozzle. So, ito yan. Okay. So, we have here that is 50 mm. So that is equivalent to 0.05. That will be in terms of meter. Yeah. Then I have here my point 1. Then I have the velocity v1, which is 5 meters per second. Sorry, this is 15. Okay. 15 meters per second, which is being with an angle. So we have here your curved angle of your, this is 60 degrees, and our vane, okay, velocity prime, so that is 6 meters per second. Okay. Then I'm gonna name this one my y coordinates and this one is my x. So let's try to determine what will be the x and y components. So let's try to draw our initial direction of your force. So initially I'm gonna draw my direction of force towards there and going to the right side, and this one going down. So I have here my f of x and my f of y. Then I have my resultant, which is in this direction. So this is my resultant. So I have my resultant force acting in this direction. So initially let's assume the reaction direction is on this one. So later on we will determine so if my assumed direction are correct. So for my relative velocity, okay, for my relative velocity, I have this one. So I have my v1 and I have my v prime here. So my relative velocity, that will be v1 minus your v1 prime. So this is 15 meters per second minus 6 meters per second. So you have your u, which is equal to, that will be 9 meters per second. Now at point 2, okay, so remembering that we have this from a previous lecture, no? So remembering that neglecting the friction, no? The relative velocity of the jet with respect to the vane remains unchanged while it flows from points 1 and you will have your point 2. This is now my point 2. And rename this one as my point 2, so that my jet leaves the vane with a relative velocity u. So I'm going to draw my relative velocity here. So this is my relative velocity. Pointing in the direction. So this is my u. Now, so I'm going to draw here also my line representing, okay, so let's try to draw the line for my absolute velocity, or you say the velocity v2. Okay, so this is my v2, and initially we don't know at what angle is v2, but the relative velocity has an angle of 60 degrees. Okay? So let's draw a line here also for my horizontal component for my B2Y. So this will become the total length of this one will be B2Y. So this is my B2X. Okay. The total length from here going there. No? Then I have call this my B prime. This one. Okay, so that will be the velocity of the vane. Okay. Then I can project my line for the relative velocity pointing towards here. So they are the same on this one and this one. They are equal. Okay. Then what I don't have here, no, is this value. So I'm gonna name this one as an value of A. No? I'm gonna name this one as a value of A. And this one is velocity prime, and I'm gonna draw my line here to close my triangle here. Okay. Now the angle, the relative velocity, so that will be this is theta, which is 60 degrees. No? So let's try to represent this one, your theta, which is 60 degrees, and this one ang hindi natin alam, which is unknown, which is your beta. So the angle of your velocity 2. And this one is also equivalent of 60 degrees. So this is your theta, 60 degrees. So we can say that our velocity 2x is equal to b1 prime. So we can say that, so I'm going to write here that our velocity 2x is equal to your velocity prime, velocity of the vane, and plus the value of A. Okay? Where your value of A, so we can compute that one. So this is now, I can say this is my y component, or let's try to draw it here also. So I can draw here a line. So just only to represent my B2y, and then we can project this one here. We have your B2y also here, the same. No? And I can say that my A, no? So this is also your U. Okay? So we can say that your cosine, no, of theta, so this is ka, which is your adjacent, you have your A, and your hypotenuse of this one will be U. No? So that is the relative velocity, which is also equal to the value of this one. Okay? Then we can say that our A is now your cosine of theta times the value of U. So we can substitute this value here. We have now your B2x is equal to velocity prime plus the U times or relative velocity times the cosine of theta. Now remembering from my previous lecture to get the reaction force. So we have your equation for your f of x. So that will be the density times the volume flow rate. Okay, that is multiplied by velocity. Now for the moving vanes, no, velocity 1 component, or velocity of 1 x component minus your velocity 2 your x component also. Okay. So this one, okay, where we can substitute these values here. So we have your f of x, we have your density, volume flow rate, velocity 1x minus the value. We have your velocity prime plus u times the cosine of theta. And we can further expand this one as your f of x, density, volume flow rate. Okay. Or we can change this one also as your area times the relative velocity. So this is 1 would be 1, so 1x component is of 1 prime plus the value of this one, so that will be, so velocity 1 minus your velocity prime, then multiply by cosine of theta. Okay, so I'm gonna close parenthesis this one. And we forgot, so I'm gonna correct this one. So let me correct this one. So this is supposed to be, if you're going to substitute, so this will become your negative value. So since we're v of x, substitute will be negative. So let me correct this one. So I'm changing this one to negative. So this is also negative. Okay, negative, negative. Okay, so we're good to go. So we can further express this one. So we have your density area. So we can expand this one also as your velocity 1 minus your velocity prime. No? Then close parenthesis this one. So we have your velocity 1x. So this one velocity prime. No? Then we can also expand this one also as your, that will be minus your velocity 1 times your cosine of theta. Then this will be plus. Okay? It's negative, it will be plus. So that will be velocity prime cosine of theta. So we can combine the common terms here. So we have your f of x, density area. So this is the velocity 1 minus the velocity prime. Then this one, we have your velocity 1x minus your velocity 1 times your cosine of theta. Then we have minus velocity prime. That will be plus the velocity prime. We have your cosine of theta. Close parenthesis, this one. Where our velocity 1 of x is equal to your velocity 1. So we can combine this one also. So we can rewrite our equation as your density area, velocity minus your velocity prime. Then we can factor out here. So this will become your close parenthesis. So this is velocity 1, times we have your 1 minus your cosine of theta. Then this one, we can factor this one also. So we can say that this becomes velocity prime, velocity prime. So that will be 1 plus your cosine of theta, then close parenthesis. Then we can further factor this one. So we have your density area, the velocity 1, velocity prime. Then this one we can factor. We have your velocity 1 minus your velocity prime. Then I'm gonna close parenthesis. I'm gonna multiply this one so we can factor the 1 minus cosine theta. So that will be 1 minus your cosine of theta. So close parenthesis. And this one is u and this one is u. So let's say this, we can express density. This is relative velocity. Okay? And this one is your relative velocity also, times 1 minus your cosine of theta. So finally, we can rewrite this equation as density times your area. So we have your u squared times your 1 minus your cosine of theta, or let's say this can be expressed as density area velocity squared times the not velocity squared, so let's try to expand this one by velocity 1 minus your velocity prime times the 1 minus your cosine of theta. Now we can substitute the values here. So we have your f of x, this is our density, so that will be 1000. Oh, sorry, this is 1000 kilogram per cubic meter. Then I'm gonna multiply this one by my area, pi over 4. Then the diameter, so that will be 0.05 meter squared. and multiply this one by 1 minus your cosine of theta, which is your 60 degrees. Okay. So finally, we have the value for your f of x. Okay, I forgot to include the relative velocity here. So this is squared. Okay, correcting that one. So let me correct that one. And RU, so that will be 9 meter. No? 9 meters squared. Okay. So I have my value which is equal now to 79. So that will be 79.52. So checking my units here, so we have kilogram, meter squared. So cubic cancelled out. So checking my units, so I have the value for your f of x, which is Newton. So let's go for your forces, reaction force along y. Okay, so we have your f of y, so that will be equal to density molecular rate. Then we have your velocity 1y minus your velocity component 2y. So your velocity 2y here, so that is pointing what here. So velocity 1y is equal to 0. So because we don't have the reaction, or say the flow is purely horizontal flow, so we don't have a flow that is on this y direction. Okay. So this is eventually will be cancelled out, it will become 0. Now for the velocity 2y, so we can say that this is the sine of theta. No? So referring to the triangle here, so we can say our velocity 2y, so that will be sine of theta. Okay. Then we have your, that will be so your opposite, so that will be velocity 2y divided by your hypotenuse, which is your relative velocity. Then we can say, further say this one, we can rewrite our equation. So your velocity 2y now is equal to your, so that will be u. So u sine of theta. Or we can express this one by the velocity 1 minus your velocity prime. So then substituting this one to my equation, so we have your force at y, so that will be density, and we can express this one also as your area, relative velocity, minus your u, or relative velocity sine of theta, and your f of y, or force of resultant component, force component of y. So we can say this is a negative value, density, and your area, we have the relative velocity squared times the sine of theta. So you'll notice that we have here your f of y, which is pointing downward. So it means that our assumption is correct. So that is negative. And okay, let's try to substitute now the values. We have negative, so this is will be 1000 kilogram per cubic meter for the units. Then multiply by the area, that will be pi over 4. Then you have your diameter, that will be 0.05 meter. So I'm going to raise this one to squared. Then multiplying the relative velocity, which is 9. No? 9 meter per second. So I'm going to raise this one to square. Then multiplying by theta, the sine of theta, or sine of 60 degrees. So we have now your f of y, or force at y component, is equal to, so I have a value of which is negative 137. So this is 137.73. So that is Newton. Okay, so that is negative, that is pointing downwards, or let's say this can be as 137.73 Newton. That will be name, or example, we can say this one is downward. Okay. So that answers the questions here, the x and y components of the force. Now, if you want to compute the resultant force, so we can also try that one. So for your resultant force, so that will be your force is equal to the square root. So that will be the square root of your so that will be your f of x. So I'm gonna square this one, and your f of y, I'm gonna square this one also. So for our force, so we have the values for the f of x. So that will be, so that is 79, no? 79.52 Newton. So I'm gonna raise this one to squared. And for your f of y, so I'm gonna place here, even if I place here negative, so I'm gonna square that one, it will be also positive. So square that one. So pressing my calculator, I have the value of my resultant force. So that is, I have the value of 159. No? That will be 0.037 Newton. Now we're looking for the direction of the velocity it leaves jet. So we're looking for the resultant not the result yes, the resultant velocity of v2 or v2. Okay, so we can express the equation. We have your v2. Okay, so that will be equal to the square root. So that will be square root. So that will be square root of your velocity 2x squared plus your velocity 2y squared. Now for the velocity 2x, so we can say that our velocity 2x, so that is equal to velocity prime plus the relative velocity times your cosine of theta. So substituting the values here, you have your prime, so that will be 6 meter per second. Then our relative velocity, that will be 9 meter per second. So multiplying this one by cosine of theta. So this is 60 degrees. Cosine of 60 degrees. So we have your velocity 2x is equal to. So I have the value of that is 10.5. No? So this is meter per second. Now for the velocity 2y, so we have here, no? The equation for velocity 2y, so that will be equal to the relative velocity times the sine of theta. So we can substitute the relative velocity, which is 9 meter per second, then multiplying this one by sine of 60 degrees. So we have the velocity 2y. So I have the value of that is 7.79. So this is meter per second for velocity 2y. Now we have to complete the value 2x in your 2y, so we can directly now substitute it in here our velocity 2. So for our velocity 2, so we have here the square root. Okay. So that will be 10, no? 10.5 meter per second. So I'm gonna square this one, then adding 7.79 meter per second. So I'm gonna square this one. Then our velocity 2 is equal to. So I have here a value of velocity 2, which is 13.07. So this is the unit of meter per second. Okay, so that answers the velocity as it leaves the jet, okay? Or as it leaves the vane. Now next, we need to determine, so what will be the beta angle? So at what angle does the velocity 2 leaves the jet? So that is, the equation for that one is simply as your tangent. No? So tangent of your beta, or your, say this is, okay, that is beta, that is TOA or tangent. So we have your opposite, so we have velocity 2y divided by velocity, which is your adjacent, which is the velocity 2x. Now directly substitution, so we have your velocity 2y, which is 7.79. So the unit is meter per second, then divided it by velocity 2x. which is your 10.5 meter per second. Then finally, we have the value for your angle. So we have the value of that is equal to 36.57, okay, degrees. So again, checking here, no, your beta and the angle of the relative velocity. So you will notice here our relative velocity as it makes an angle to the horizontal axis of this of 2x. So that is 60 degrees. Now you will notice here if our solution is correct or not. That you will notice here that our angle of your beta, which is only 36 degrees. So this one falls inside, no, that this is in between the or included, so sakop pa siya ng 60 degrees, which is your 36.57 degrees. Okay, so let's try to highlight our answer to the problem. So I have this one and I have this one for f of x. So this is only just included soon. So dinagdag ko na lang. I just included this one. But it does not answer to the problem. We're looking for x and y. And this one also answer, and this one. Okay. So that concludes the solutions for this problem. So I hope you fully understand. So that's it. Thank you.